Hi, everybody. I'm John Tudleski, and I'm the Director of Rapids Machine Learning at NVIDIA. Today, I'll be talking about how to use GPUs to accelerate your machine learning model tuning with Rapids and MLFlow, all integrated with the Databricks platform. So first, I just want to say that all of the resources for this talk are available at this GitHub link up here at the top. So that's github.com/rapidsi/cloudmlexamples. That includes the notebook we'll walk through live a little later, some READMEs, and other getting started materials. So feel free to open that up and follow along in the background. So where's this talk going to go from here? We're going to start by motivating the problem of what is hyperparameter optimization? What are some of the challenges with it, and how can we solve them? Part of that answer is going to be using Rapids machine learning. So we're going to dive into the details of Rapids ML and the Rapids platform so everyone gets a basic grounding there. Now, we'll talk a little more about how we've integrated Rapids together with MLflow and HyperOpt to make this model tuning process and all model management really seamless. But we're going to spend a lot of our time together, not just looking at slides, but really diving into a demo notebook, which again is also available at that repo. So we'll save about half of this talk to jump into the code. So what problem really motivated this set of tools to come together? I've been a data scientist for a while, and I think a lot of my life has kind of looked like this, that you've prepped a lot of data we're really excited about. We defined some key metrics for a model. We built a model, and we were really excited about it, but the accuracy, maybe it's not quite good enough. Maybe we have a feeling that we could do better. Or maybe we just know that it's a model where increasing accuracy is going to deliver a lot of business value. So what's the next step we do here? Well, typically, we might look at changing some of the hyperparameters for a model. Many machine learning models are quite complex and have a huge range of hyperparameters that we could tune. We can play with some of them manually. So if I look at XGBoost, for instance, a popular gradient boosted decision tree tool that has about 25 plus parameters that go into a model. And I work on XGBoost pretty much every day, but I think I sometimes forget what half of these parameters mean, to be totally honest. And it can be really a slog to dig through them. So we could manually tune everything. You could spend days kind of tweaking parameters, trying out the increasing tree depth or whatever other parameters you want to play with. But that quickly becomes a massive time sink. And it seems the kind of thing that maybe computers could do a little better. So that's option B, which is automated hyperparameter search. This is best represented in Databricks by the HyperOpt package, but it's really an idea that goes back further in academia and is starting to be increasingly used throughout industry. So hyperparameter optimization, or HPO, is pretty simple, really. We're going to train and evaluate many, many model variants in parallel, possibly hundreds of model variants, trying out all kinds of different combinations of hyperparameters. And we're going to use some process to automatically pick the hyperparameters that deliver the best model. It sounds simple in practice, and it's really nice that we don't have to do that much work to get better accuracy. Often you can take some existing scripts, layer them together with a hyperparameter optimization library, and just kick off hundreds of models, which is really exciting. But the challenging part is that hundreds of models part that I mentioned. We're going to have to manage those models. We need to keep track of what are the best ones, what was the exact code used in each one, and we have to wait for hundreds of them to complete. So that could turn to be a challenge. Maybe it makes our workflow much more complicated if we don't do this right. So I guess I want to convince you here that it is possible to do this well. It is possible to make it easy, but we really need to integrate three components. We need an HPO framework that makes it simple, so you don't have to go write a ton of new code in order to do hyperparameter optimization on your existing model. You need something that's going to manage the model lifecycle, so that when you train these hundreds of models, you can easily go back and find the best one, find how it was trained, pull it out, and then go use it for inference when you need to. And I think one of the key pieces that's often been missing in this is that you need really fast model training. If your model takes an hour to run, but you want to run hundreds or thousands of variants of it, suddenly your lunch break problem has become a week-long problem to tune. And that may be absolutely unacceptable. So Rapids is really one of the key missing ingredients here because it accelerates machine learning models pretty dramatically. So one of the experiments we'll walk through in a sec goes through a simple hyperparameter optimization example, building a random forest classifier for a decent sized data set. We did that with just CPU in scikit-learn, and it takes about 7 hours to complete a simple hyperparameter sweep. With the same configuration in Rapids, that gets down to 17 minutes. Again, training the same sort of random forest and using the exact same hyperparameter optimization. So this turns something from a day-long problem to tune your model into a coffee break problem to train your model. We think this is the kind of thing that's going to make HyperOpt much more accessible and much easier to integrate into your daily flow as a data scientist. But before this makes sense, probably we want to talk a little about what is RAPIDS? How does it fit in with the Python data science ecosystem? So here at the Spark AI Summit, you'll hear other talks too about how RAPIDS integrates directly with the Spark ecosystem and can be available to Scala users as well. Here we're going to focus primarily on the Python side of RAPIDS, which targets data scientists who are already familiar with a Python stack kind of like this. I think if you build models in Python all day, you probably know most of these libraries. So Pandas for your ETL, scikit-learn, NetworkX, deep learning libraries like PyTorch, maybe Dask for distributed computing, and all kinds of visualization libraries. When we went to do RAPIDS and to build GPU acceleration for data scientists, we said, why reinvent the wheel? Why make people learn a whole new set of APIs when we can match these existing APIs that are already popular with millions of data scientists? So that's essentially what we've done. RAPIDS mirrors that existing PyData ecosystem, but builds GPU-based backends to accelerate each of those libraries on GPU. So instead of using Pandas for ETL, now you'll use cuDF for ETL. Instead of using scikit-learn for machine learning, now you use cuML, but you have the same APIs that you're familiar with. It just goes much, much faster because everything is in GPU memory, all integrated with a common format based on Apache Arrow. Why do we care about moving data science onto the GPU? Well, the hardware advantages of being on a modern GPU are pretty enormous. Even from the voltage generation of NVIDIA GPU, you can get about a terabyte a second of memory bandwidth, which may be 20x higher than you can get in a CPU platform. You can have 15 teraflops of performance in a single card, and you can have incredible interconnect speeds between cards, either on the same machine or across machines. You can continue to scale your problem up. But it's really an amazing beast of compute power that deep learning scientists have been using since the beginning of the modern deep learning age. But other data scientists haven't always been able to take advantage of because the libraries weren't there to use this sort of compute beast for your ETL and for your traditional machine learning. And that's the problem that RAPIDS really meant to solve. So when we look at the core building blocks of doing Python data science, it usually starts with ETL. Usually starts with something like a Pandas type problem. And I think we all know that as much as many of us spent time in school learning machine learning, 90% of our time can go to ETL and data munging. So we've all been there that your simple batch job to add a few more features to your large data set suddenly takes another 15 minutes, found there was an error, you've got to iterate and repeat. We can spend tons of time on these iterative ETL workflows, and that's why we built cuDF to accelerate that. So if you're familiar with Pandas, this API example over here on the right should hopefully look very familiar. This is actually using cuDF, and all of this work is happening on the GPU. So here we'll load this file onto the GPU while it's still compressed, decompress it on GPU, and do a lightning fast GPU-based read of the CSV. It was kind of surprising. I think the first time I started playing with this, I would have thought that maybe there's not much more you can do to speed up reading CSVs. But even something as simple as this, we're talking 20x speedups over what you can get in a CPU. So here you can do all the sort of standard Pandas functions, string manipulations, simple column data type changes, turning something into an integer. These are the sorts of things we do every day as data scientists, but we want them to be much faster. And they are much faster when we switch things over to a GPU. So here, just running simple workloads like merging data frames together, cuDF can run 500 or 900 times faster than Pandas. Sorting columns, doing group bys, these are the things we do every day as data scientists can have a factor of several hundred speed up just by moving into GPU while being API compatible. This is something that enables you to do so many more experiments in your pipeline. And when we bring together that the traditional machine learning from RAPIDS ML, we can help complete the picture. So RAPIDS ML, or especially its central library cuML, fits in right where scikit-learn does in the PyData ecosystem. It's really a suite of machine learning models that are easy to use, all based on a reusable core CUDA foundation. And these libraries that CUDA and NVIDIA have been optimizing over the past decade. So what does it really look like to use cuML? Well, this is sort of a standard machine learning 101 problem, right? All done in the PyData ecosystem. Load a data set, put it in Pandas, run a clustering algorithm, and then plot the results. So we can cluster these points into two different subcategories. Many of us have written this several times, and now if we want to port it to cuML and cuDF, we've highlighted all the changes that you need to make here. You can see essentially all you had to do was change a few imports here. But we really, really closely manage API compatibility with these existing libraries. If we're incompatible because we're missing a feature, because we have a slight difference in our API, we consider it a bug. Please file it. We're going to jump right on it. This is something we take very, very seriously. So what do we offer within machine learning? Well, pretty much the most popular versions of traditional machine learning algorithms that data scientists use every day. So that includes tree-based models like decision trees and random forests, linear regressions, nearest neighbors, dimensionality reduction. Some of those, like UMAP and t-SNE, can become really beasts to do. It can take a huge amount of time on CPU. So having these speedups really transforms where you can use them. We talk about speedups. We talk about anywhere from 5 or 6x for the simplest possible models up to speedups by a factor of over 700 when you're talking about support vector machine models or dimensionality reduction. Typically, as your problem gets larger and more compute intensive, once you scale up to these 4 million, 20 million, 200 million row data sets, you start to see a much, much bigger gain from RAPIDS as you can finally take advantage of that huge compute beast that is the GPU. So one of the additional libraries that we work closely with in RAPIDS ML is XGBoost, which is one of the most popular tree-based machine learning libraries. XGBoost 2 fits into this GPU ecosystem and allows you to load data directly from cuDF or from other GPU-based data formats without having to do a round trip through CPU memory. Again, just by enabling GPU acceleration, you can get these huge speedups up to 17x depending on the data set that you're fitting on. So XGBoost fits in the same way as cuML does to the rest of this ecosystem too. There's way more about RAPIDS than I can possibly go into in this talk. I really encourage you to check out rapids.ai for a much deeper dive. But here I want to shift focus and really talk more specifically about how RAPIDS integrates with MLFlow and HyperOpt and how we use all of those in a Databricks environment. So I know there are many more talks at the summit about MLFlow, but just so we're on the same page, MLFlow is really about machine learning model lifecycle management. It allows you to track your experiments so you know exactly what code, exactly what git hash was used when you train a model. It saves the parameters and logs that went in that training so you can reproduce that or analyze if something went wrong. It lets you persist your past models in a centralized model management database so you can query them again whenever you need them. You can visualize models side by side like we're doing over here. And you can convert models so that they can be used and deployed in production, which I think is one of the most exciting features of MLFlow. Finally, MLFlow is deep integration with the Databricks platform, and now it has integration with the RAPIDS platform as well too. So you can dive much more into MLFlow with either of these links here at the bottom, but we'll also show more about it in the live demo that we have. What does it look like though to integrate RAPIDS with MLFlow? Well, since the beginning of MLFlow, it's had support for scikit-learn models. So you can see over here on the left what a typical scikit-learn flow would look like. Essentially, we're training a model, and then MLFlow enters after we've done the training. We want to log some metric. So we measured how accurate our model is. We log that so it's persisted along with all the artifacts of this model, so we can query it later and figure out what that accuracy was. We're also logging the model itself. Here, this model will be pickled in Python terminology and saved to a central model database. So you can always unpickle it and then go do inference, go do further inspection or training later. Really easy to use API. MLFlow is very lightweight and easy to add to your workflow. If we're going to do this in a cuML workflow, well, we've really faithfully matched the scikit-learn API. So you find we can do the exact same thing. You can use the accuracy scores that are developed in cuML, log those metrics exactly the same way. And you can even use the exact same scikit-learn interface to log a model, knowing that this is just a GPU-based model that was developed with RAPIDS. And it works the same way as scikit-learn, but it was trained much, much faster, as we'll see. You put all this together and integrate it with HyperOpt, which is the third piece of the puzzle that we talked about initially. So we already have really fast model training with RAPIDS, and we already have a way of managing model life cycles with MLFlow. HyperOpt does the actual exploration of your hyperparameters. So it's an academic project originally that's gone on for a long time, but it's become increasingly popular in industry and again has great integration with Databricks. It uses a clever algorithm called tree structure partisan estimators to allow you to explore all of the possible hyperparameters in an intelligent way that balances between the needs to do exploration, that is trying very different hyperparameter settings that you haven't tried before, but also exploitation, which is once you have some pretty good hyperparameters, let's try some pretty similar ones and see if we can get a little more of a local optimum there too. So really cool algorithm to read up more in the detail. But I think for the purposes of training a model, it's actually really simple. You define a model function here that trains your model and evaluates it and basically returns your evaluation score. It's going to take in the hyperparameters as this params tuple. You choose a parameter space, that is, what's the range of hyperparameters you want HyperOpt to search over. In this case, imagine we have a hyperparameter called x. We're telling it to search between -10 and 10 as reasonable values for x. Then you just let fmin rip, and it's going to go run, in this case, 100 different versions of your model and find the one that delivers the best accuracy score as you've defined it here, and we can print that out here. On Databricks, this can all be done in parallel to over many workers, which makes it particularly cool and scalable. So we want to dive into the actual demos and really get into how this works in a more complex example. But again, I'd encourage you to look at the GitHub repo here that has examples in much more detail. If you want to run Rapids on a different platform, try one of these resources below, either our GitHub page or Conda package to get started. Or if you work in a Docker-based workflow, NGC, the NVIDIA GPU Compute Cloud, already provides optimized Docker images that you can build on. All right, now we get to the fun bit of the talk where we're going to actually dive into the code. So I just started with this basic Databricks landing page that you've probably all seen in the UI. And now I want to go and make sure I have a cluster set up that can run Rapids and actually let us launch a notebook. So I'll go over to the clusters UI here. I've already defined a couple of these clusters, but it's worth looking into exactly how to configure a cluster so that you can use it for Rapids. Now the core of Rapids, of course, is to be able to use GPUs for data science. So you want to go here to the Databricks runtime version and make sure you've selected a runtime that's compatible with GPUs. So here I'm using a 6.6 ML runtime, which clearly shows that it's GPU compatible. You can select one of these other GPU compatible runtimes too. It's also critical to make sure that we've chosen workers that actually have GPUs attached to them. So this is an AWS backed cluster, so you'll see some AWS instance type names. There are a ton of options, but you just need to focus on the GPU accelerated section. Any of the G4DN or P3 based instances will be fine to run Rapids. They're all modern GPUs, and you can choose what fits your workload best based on cost and kind of throughput of the GPU. Here I'll use a P3 2x large, which contains 1 voltage GPU. It's kind of a nice starting point for training. And I'll make sure my driver nodes have the exact same instance type. Now, Rapids doesn't come pre-installed in the Python env that comes with this Databricks runtime, but it's really easy to set up. In that Cloud ML examples repo that I mentioned earlier, we offered a init script that does all of the installation you need for your cluster. So you just want to go into advanced options, go to init scripts, and make sure you've added the init script from the Cloud ML examples repo that installs the version of Rapids that you want to use. Here we're installing Rapids 0.13. Just downloaded that to DBFS and then added this init script. That'll run when the cluster node starts up and automatically do a bunch of Conda installations, get you the Rapids packages you need. So again, pretty seamless. Just grab this init script from our repo. Now let's actually look at the real code and walk through a bit of a more realistic example. So this is going to be a simple example of building a classifier for whether a flight arrives on time. I think a lot of us are kind of missing those days when we used to actually fly to conferences like Spark AI Summit and get to meet you all in person. So it's nice to do something travel related here. We start with a couple of Python preliminaries, just importing the critical packages. And we'll do both scikit-learn and QML versions so we can do some comparisons. We added some logging functions just so that we can share the timings of various things. And we'll start by loading some of the data. Here we have a 20 million row example of the airline data in Parquet format. And we also have a 1% subsample of that. It's airline small data set. We'll use the 1% subsample just for this interactive demo, but also post the larger data one online so you can see how much bigger the speedup gets as you go to larger data sizes. So we can read this in with cuDF as if it were Pandas or anything else. It's just much faster. So even though the read happens on GPU, we can print this out easily in the notebook and see it's a pretty straightforward data set with metadata, 1 row for each flight, and a simple binary variable. This is what we're going to want to predict is arrival delay binary. This is 1 if a flight was delayed and 0 if a flight arrived on time. So it's something that we kind of nice to know in advance. So to predict this, we often like to start with a random forest classifier. This is one of the most popular models in data science. Just going to build an ensemble of trees and use those to predict. You can see though that the scikit-learn version has quite a few options that you can dig into as you go about optimizing. We could dig into all of these manually, but it'd be a lot nicer to have hyperopt kind of solve the problem for us. Here we're going to focus on a couple of the critical parameters. Max depth. So how deep do you want each tree to be that gets built? Max features. So every time you split a node, do you want to look at all the features or just a subset of them? And also the number of estimators. So that's how many trees we're actually going to build and can determine a bit about whether we overfit and or underfit. So there's the 3 really classic parameters that can make a big impact here. Let's start by looking about how you do this in scikit-learn and integrate scikit-learn with MLFlow and hyperopt. We start with a really sort of simple scikit-learn pipeline in here that could be in any script. We load in some input data, extract the target, split to train and test, build a classifier, and then evaluate it to find its accuracy. Probably something we've all done 100 times as data scientists. The parts here that are interesting are, one, we start by using MLFlow. So here in MLFlow, we're going to log the model after we've trained it. This means that the model we train will be persisted and sent to a central model server through MLFlow, which in this case is also managed by Databricks. That means that if we ever want to do any additional debugging or deploy this for inference, we can easily go extract that out of the model database, which comes in really handy. We're also going to log a metric from MLFlow. You can log as many metrics as you want for a model. You might care about, for instance, both accuracy and precision and recall, for instance. In this case, I'll log just accuracy, and I'll also have to return something that HyperOpt can optimize. So in this case, HyperOpt is going to minimize something for us. So we want HyperOpt to minimize the opposite of accuracy, or maximize accuracy effectively. This is just wrapped up in a real simple function that takes in a tuple of params and can be called by HyperOpt. But there's really not a lot of wrapping that you have to do about it. You just kind of crack open these parameters and make sure you understand, you return a loss that HyperOpt understand. So before we've been running this, let's look at what it's going to take to port that to GPU. And this is just a RAPIDS version of the exact same application. You can see the only differences really are that we're using cuDF to read the data. We're using cuML to pre-process and train and to compute metrics. But otherwise, these are all just import changes. We haven't changed any of the parameters. We haven't had to do any additional work. It was really just literally a copy paste and mechanical transfer. Again, we can use the exact same MLFlow functions. You can log a model to MLFlow if that model was trained on GPU really fast, or if it was trained much slower on CPU and scikit-learn, it works the exact same way, which is part of the advantage of this set of workflow. And again, we'll return our loss function too. So let's see how long it takes to do this on CPU. I just grabbed some totally arbitrary parameters, and it's about 100 trees of depth up to 8 on this small data set. So we're printing out a couple of timing stats for each of the different stages here. ETL is fast, the loading is pretty fast. Fit took 7.7 seconds. It's not the end of the world, but this is a 1% sample of our data, and we built a pretty small model on it. So we can see that this is going to get to be a pain as we move to our full data set, and it's really going to be a pain when we run HyperOpt, and we want to run hundreds of versions of this. So let's say we just try and do the same trivial example with the RAPIDS version. How much faster is that? Okay, that was returned a little faster. And here we can see that fit was a little more than 20 times faster on this small data set. It's only down to 0.35 seconds there. So really feels like no waiting time. And this speed up is going to scale up even further as we go to larger data sizes, which is a very typical thing we see within RAPIDS. So now we plug everything into HyperOpt, just as we showed in the slides. We're defining a real simple space to search for parameters. We just tell it what's a reasonable range of max depth, reasonable range of max features, and a reasonable range of n estimators. And HyperOpt will do the actual exploration within this for us. So we can set this up with these parameters, and we'll actually use these exact same parameters for both the CPU version and a GPU version. In either case, one key thing to know is that for the Databricks version of HyperOpt, you want to start by defining a Spark trials object. This is basically a placeholder that will keep track of all your trials and integrate them with the Databricks UI. Now, I'm not going to run the CPU version now because it actually takes a super long time, unfortunately. Let's jump right in and try and do this with the GPU version here. Again, you can see the code for GPU, though, is essentially identical to the CPU. We're just using different naming so we can keep these things straight in our model registry. So we kick this off, and it run the fmin function from HyperOpt. Fmin really is the main driver that kicks off this search space, search process with all these jobs. And we can see right away in the UI, it's starting to run 2 jobs in parallel. These will automatically be tracked within MLFlow, and you can see they're starting to complete already here. And we can grab them easily up here in the runs section of our UI. So if I go to the top and click on runs, I can see all these past runs, and I don't just get a job ID or the date. We're actually seeing what are the features being explored by MLFlow, which I think is pretty cool. That said, this interface can get a little bit confusing, especially if you have a large number of runs. There's also the much more detailed experiment UI. You can get to that just by clicking at the bottom here of the runs UI and pull it up. Here it's going to show all of our past runs. So we've got lots of experiments here, but let me just take one kind of large set of runs that I ran previously. I don't want to have to click each one of these by itself, but so I can just select this whole region of runs. These were all a bunch of different hyperparameters that we tried running. So they have different max depth, you get different accuracy, and all the other hyperparameters were varied too. The best way to see it though is not to use this UI, but rather to go to the compare UI after selecting some of these. Now you get kind of a deep dive into each of the past runs you did. These were all the parameters set for each. Here's the accuracy you got out of it. And we can already see, just looking at the first couple of these, that you can start to gain accuracy pretty quickly from some of these defaults. From, we're going to vary down from the 8.3s down to around 8.6 for the best models. Helpfully, it includes a scatter plot where you can look at one of the hyperparameters and see how accuracy varies, for instance, as we vary max depth. You can kind of begin to see this upward trend here. Or we can look at all of the hyperparameters at once, this max coordinates, with this parallel coordinates plot. We start to see the range of a couple of points of accuracy between a random model or poor model and one of the best models. So again, you can explore this UI in a lot more detail, and you can actually query these things in a rich way. But clearly what we're going to do here is pick the best version of our model and run with that. So what does that look like? Once we have a good model, where are we actually going to go with it? I'm going to start by going over here to the Models tab, and you can see there's actually this nice interface built, which is taking the models that we trained with MLFlow that we logged and registered according to a registered model name into the model registry. Here, I'll open this up, and it looks like we've trained a couple of past versions of this RAPIDS-based airline model. I'm going to go and take one of them and say, okay, this latest version 5, I want to use this as my production model. So let's transition that to production. I know it's great. We did this awesome hyperparameter sweep, and so we feel really good about it. If I have any questions about it, though, I can always drill down into the run that backed it and see exactly what was the loss and what were the hyperparameters used for it. All right, so it's a big model with max depth of 15. Makes a lot of sense. Now this is in production. What can I do with it? Well, it's very simple. Clearly, what we're going to want next is deploy this for inference somewhere. And that gets really easy, and that's where the integration with MLFlow is super helpful. So if I have some script that just wants to take whatever is the latest version of this model and have this inference script not have to know about versioning and who's tagged what as production, I can use the MLFlow client to query based on this model name and say, just get me the version of that it's in the current stage called production. So we can run that, and MLFlow will automatically figure out, here's the full name of the saved model that we've tagged as production. So this could be a completely separate data scientist who has to use this in production, who doesn't have to know about the life cycle of models we're updating in the background here. So we can just pull that model into production. Here we're going to load a model using MLFlow scikit-learn load model, and we're going to load it from that URI. And you can see what we've gotten back is actually this QML random forest. So exactly the random forest classifier that we trained previously is up and running in our driver here. And we can just go load in some data, again, drop off the unnecessary target variable, and go ahead and predict from it and see what happens. So it's going to take a sec to read this in from Parquet, but we immediately get back out a bunch of predictions, which are the predicted delay or not delay binary variables from here. So again, you can see that by hooking into MLFlow, you don't just get the ability to do hyperopt, but you start to get some of this model lifecycle management pretty much for free with just a few lines of code. One of the really powerful things here is that because we match the scikit-learn APIs carefully in QML, we can leverage all this existing infrastructure that's baked in MLFlow from the beginning and allow you to do model deployment with these much, much faster models and lifecycle management in the same way that you would with scikit-learn. So hopefully this is easy to get started, but again, play with it on your own. You can get this from the RAPIDS AI Cloud ML Examples GitHub repo.